The next topic we're going to look at is frequency compensation. So up to this point, we now know how to determine if a system is stable or unstable, and we also know how to design a system for stability. But what we want to look at how to do now is how can we make a system stable? So how can we take a system that is unstable? So let's say, how can we make an unstable system stable? So if somebody has already created a system and it turns out it's unstable, how can we make that unstable system stable? And so of course the answer is going to be by doing something called frequency compensation. So the question then becomes, what exactly is frequency compensation? So the basic idea is we're going to insert a new dominant pole in our loop gain. And so what we want this dominant pole to do is we want it to be it's typically going to be a relatively low frequency. So let's say it's going to be sufficiently low such that our magnitude of that loop gain function is equal to 1, or again, we could also say this in terms of our decibels is equal to 0. And so we want that to happen at a lower frequency. And so what do we mean by lower frequency? Well, of course, the frequency has to be before we reach our negative 180 degree phase, because that's just our definition of stability. So again, like with most things, this is a little bit confusing if we're just looking at words. So let's have a look at what this looks like in terms of plots. So here I have a Bode plot, both magnitude and phase information for some three-pole system. So if we look closely in the magnitude, for instance, we can see we roughly have three regions with different slopes. We have a 20 dB per decade, a minus 40 dB per decade, and a minus 60 dB per decade. And down here in our phase information, we see that we're sort of stepping through at our corner frequencies, going from one pole is contributing negative 90, a second pole another negative 90, a third pole another negative 90, so that overall we're ending at a frequency of a phase angle of negative 270 degrees. Like with previous plots that have been stacked vertically, I've attempted to sort of line up our frequency axes so that we should be able to draw these lines between the two plots to compare points. So what we notice then is, again, keep in mind our key phase to check for stability is negative 180 degrees. So we can come here, we can say this is the point where we have negative 180 degrees in our phase. Follow this dashed purple line up and we can get the corresponding magnitude of our loop gain function. We notice in this case that the loop gain magnitude in decibels is greater than 0. So let me write that up here. So we have our magnitude of our loop gain in decibels is greater than 0 at our phase of negative 180 degrees. And so of course, what that means is that this system is unstable. So we have this unstable system. We want to do frequency compensation in order to make it stable. From this basic procedure up here, we can see what we're going to do is insert a dominant pole. And we want it to be sufficiently low. So just to make it sort of easier to see, let's make this dominant pole really low. Let's insert a pole at 10 hertz. So let's say we're going to come back to this system and we're going to insert or add a dominant pole at a frequency, and I'm going to call this frequency F sub PD, F sub dominant, pole dominant at 10 hertz. And so let's come up here and see how that changes our Bode plots. So remember, and so let me go ahead and note here, our blue curve is going to be our uncompensated, or our original. And let's then do our new curve in green. So this is going to be our compensated Bode plots. Okay, so remember for our basic Bode plots, if we're doing our simple approximations, we're going to have our low frequency gain up until we get to our new sort of cut-in frequency, which is going to be 10 hertz, after which we're going to be decreasing at 20 dB per decade. So up until this point, we have the same curve as we did with the blue. And then to make this line up with my notes, let me try to. So you'll note here that we had roughly this second pole at around 10 to the fourth. So I can draw a line here that's roughly a negative 20 dB per decade slope. So roughly the same slope as this segment right here. And after that point, then we'll be decreasing at negative 40, and then negative 60 a little further on, and so on and so forth. So what does this do? So that's how we change our magnitude plot, but what is this doing to our frequency plot? Well, what we can see is now at our first corner frequency, we should be at negative 45 degrees from our approximation. For our second corner frequency, which was about 10 to the fourth, we said, we should be at an angle of negative 135. And so that's because these poles are very far apart. So 10 times this first corner frequency of 10, which is 100, we should be at our negative 90. So here we're at negative 90. 10 times our second corner frequency, so at 10 to the fifth, we should be reaching our negative 180. So around here, we should be crossing over 180. And we're going to continue to decrease past that. So let's redraw sort of our new curve here. So maybe it looks something like this. And so again, I'm just trying my best to draw an approximation here. So if you want a more exact look at this, you can of course see what is drawn in the textbook. So we have something that looks like this. And so that'll keep on going down there. So again, the key thing to note is that now we've changed this frequency at which the phase is equal to negative 180. So what we can do is we can draw a dashed line up from here now. And so let's say that was around 10 to the fifth. And so even before we get that sort of set up correctly, we can see that our magnitude of this loop gain function is going to be well below our 0 decibel limit. So let's come back here and say now for our compensated system, the magnitude in decibels is less than 0 for our frequency where our phase is equal to negative 180 degrees. And so of course that means we have a stable system. So again, to highlight here, we'd be looking at some point here, which is going to have a negative decibel value. So that's sort of the basic idea. We're sort of shifting these curves. We're making our gain function start dropping off quicker so that it gets below 0 before our phase is able to reach that negative 180 degrees. So what you might be noticing from looking at this is we do have a disadvantage of doing this. So let's come down here and write explicitly what that disadvantage is. So we can see that clearly from looking at our gain plot. The main disadvantage is we have a reduction of our loop gain. And so remember, our loop gain is just beta times the open loop gain. So we essentially have a reduction of our open loop gain for a wide range of frequencies. So let's go back up to our plot and see where that is. So basically the part we're talking about is right here. So if we compare our green and blue curves in these regions, we see that along the green curve, we have a lower gain than we did on our original blue curve. And so of course, if we make that pole, that dominant pole that we're introducing a larger value, this green dot is going to be shifting over here, and we're going to be able to maintain that higher gain for larger frequencies. However, if we shift it too far, if our dominant pole frequency is too large, of course that means we are getting closer and closer to the system being unstable. Another thing to keep in mind though, that sort of goes along with this disadvantage is yes, we have a reduction of open loop gain, but remember we talked about something called the gain bandwidth product, and we said that our gain bandwidth product is ideally constant. So what that means is that if our gain is being reduced for certain frequencies, then our bandwidth should be increasing. So like with most things, there are trade-offs. And so we're not going to go into a lot of details, but if you're curious about some more details about that trade-off there between our gain and our bandwidth product, you can look at pages 920 to 922 in Niemann. What we're going to do in the next video is look at a quick example of how we can use this idea of inserting a dominant pole to perform frequency compensation, and then we're briefly going to talk about a different type of compensation as well.